Okay, good afternoon, everyone. So, welcome back to the second Start Right session. Now, actually, this is our first Start Right session, to be fair. This is the first session to actually give you a foundation and a flavor of what you will be learning at the start of Sec 4. Okay, as mentioned just now, okay, the Start Right sessions are to give you a flavor of what you'll be learning in Sec 4. So that means we will not be covering the whole set of notes, every single question, but really is to give you the foundation and basis to cope with the topics when you learn them in Sec 4. So when we start Sec 4, we will still go through these topics from scratch. It is just that hopefully with the foundation you have gained now, you are better able to appreciate the topic and learn the topic a little bit faster next year. Okay, so this is part of learning in advance, learning a little bit on your own in advance. Okay, now let's begin talking about redox. Now, redox is short form for reduction and oxidation. Okay, so at the end of today, you must know how do we define reduction and oxidation. There are 4 different ways in which we can define reduction and oxidation. All right, 4 different ways. Moreover, reduction and oxidation, they are the opposites of each other. That means oxidation is the opposite of reduction. Okay, so why do we shorten it as redox? This is because in every single reaction that you see for redox, there will be one thing that is reduced and another thing that is oxidized. You must have in the same reaction something reduced, something oxidized. You can never have a purely reduction reaction. It wouldn't work. A reaction must have something reduced, something oxidized. It's a bit like something loses, something wins. Okay, it's together in the same reaction. That's why it's called a redox reaction, because both happen in the same reaction. Okay, now redox reactions are actually really common around us. Actually, you have encountered this so often in your daily lives that you don't even think about it. Now, what redox reactions do you actually see around you? The most common reaction is rusting. Okay, I'm sure you have seen by now, if you leave like iron, things made of iron, exposed to air and water, it will rust, right? So iron is a metal. Iron looks like a silvery gray piece of metal, but over time, as it rusts, it forms a reddish brown solid. So if you use QA to think about it now, reddish brown means it's iron 3, right? So rust is actually iron 3 oxide. Okay, so rusting is redox. Rust is actually iron 3 oxide. So how has iron formed iron 3 oxide? Well, you can imagine from the compounds formula, you can already see iron must have reacted with oxygen in the air to form iron 3 oxide slowly over a period of weeks and months. So this is an example of redox, where iron is actually oxidized to iron 3 oxide. Okay, so that's rusting. Another common example of redox around us, if you were to cut up fruits, for example, apples, if you cut apples, you slice them up, and you leave them exposed in the open air for just a few minutes, you will realize that the apple slices will turn brown, right? Fruits turn brown, particularly apples, okay? Now, why does it turn brown? Again, this is because of the reaction of certain chemicals in the apples with oxygen. So when the apple is when the chemicals are inside the apple, they don't react because they're not exposed to oxygen, right? But once you cut the apples, the chemicals are now exposed to oxygen, and that's the reason why they become oxidized to form a brown colored compound. Okay, so these are common examples of things around us: rusting, apples turning brown when exposed to air. And if you look, this is the Statue of Liberty. You find this in New York City in the United States. Now, the Statue of Liberty is made of copper metal. Copper. Quite clearly, copper metal shouldn't look like this color, right? If you look at the Statue of Liberty, it looks bluish, greenish, green, quite green. So copper metal can't be green. Metals are not green, right? Copper metal should be a shiny reddish brown color. The metal itself is brown, all right? Okay. So what makes it turn green then? That's the question. How did copper metal, which is a shiny brown colored metal, turn into this green color? There must have been some reaction. So again, just like the example of apples just now, you think, oh, copper must have been exposed to some stuff in the air, perhaps in water, because the Statue of Liberty is right next to water. Okay, it's right next to the river, if I'm not wrong. Okay, so there must be stuff that reacted with the copper metal. Okay, so let's look deeper. The copper metal used to be a shiny brown color. Okay, now copper metal, unlike other metals, is not gray. Copper metal is one of those exceptions. Copper metal's color is really like your 1 cent coins, that kind of shiny, pinkish or reddish brown color. So copper metal used to be brown. So copper is a shiny, pinkish brown color. Then it blackened over a few years. So it's a process of years, right? So why did it turn black? So now you got to use your QA knowledge to answer this. So if you study the QA practical guide, copper 2 compounds typically are blue, right? However, copper does form a compound that is black. So which compound of copper is black? So if you go through your QA practical guide, black color solids could be copper 2 oxide. Copper 2 oxide is black. So now you think, how did copper become copper 2 oxide? Well, the answer is obvious, right? Copper must have reacted with oxygen in the air. Okay, copper must have reacted with oxygen in the air. That's obvious. Okay, now, but it didn't stop there, right? The Statue of Liberty doesn't look like a black color. The Statue of Liberty now looks green. Okay, actually bluish green. Okay, not just green. There are some hues of blue inside. So why did it turn green? Then you got to think, okay, which compound of copper is green? So you have also learned this in QA, right? Which compound of copper do you think is green? So if you go through your QA practical guide, you see, oh, copper 2 compound, mostly blue. The black one is copper 2 oxide. The green one, copper 2 carbonate. Right? So now let's look, how did copper 2 oxide become copper 2 carbonate? What must it have reacted with to make copper 2 carbonate? So looking at the formula, from CuO, how does it become CuCO3? It's quite obvious, right? It must have reacted with CO2. That's how it becomes copper 2 carbonate. All right. So where does the CO2 come from? Again, quite obvious, right? CO2 comes from the air. Okay. Now CO2 obviously naturally occurs, exists in air. Okay. For example, through respiration, we give out CO2, right? We breathe out CO2. But besides that, let's remember when you burn fossil fuels, okay, you also produce CO2. Okay. And that's the reason why there's more and more CO2 in the air now. We have learned this under atmosphere and environment. When you burn petrol, you burn coal, you burn natural gas, all these produce CO2. And that adds on to the amount of CO2 in the atmosphere, which obviously can react with copper 2 oxide. Now, why would CuO react with CO2? What kind of reaction is this? So now you're going to think, Copper 2 oxide and CO2, they are oxides, right? So this is about types of oxides. Copper 2 oxide is a metal oxide. Metal oxides are basic. Carbon dioxide, on the other hand, is a non-metal oxide. So this is acidic. So this second reaction, copper 2 oxide to copper 2 carbonate, this is not redox. This is acid-base neutralization, where a basic oxide reacts with an acidic oxide over time. Okay? Can? Now, is CO2 the only acidic gas in the air? Well, obviously not, right? Now, in the air, you also have other pollutants, especially New York City. I mean, like most cities around the world, there are many cars, there could be factories, industries in the city. So naturally, with cars, factories, you will have pollution. One of the common pollutants is, of course, sulfur dioxide. Okay, this is what you also learn under atmosphere, right? SO2 is a common pollutant. And you have learned by now, SO2 is able to react and dissolve in rainwater to form acid rain. Acid rain contains SO2 reacting with water to form sulfuric acid. Okay? So naturally, if the acidic rain were to fall on the copper 2 oxide, the copper 2 oxide will react because copper 2 oxide is basic. So you can imagine this is not the only reaction now. You could add sulfuric acid. And the sulfuric acid comes from the rain when the SO2 reacts with the rainwater and air to form sulfuric acid. So obviously this forms copper 2 sulfate. Copper 2 sulfate is not green. Copper 2 sulfate is a normal copper 2, typical copper 2 compound, blue. And that's the reason why if you look at the Statue of Liberty today, it is not green like, trees, leaves kind of green. It's more like a bluish green color because what you see today is a mixture of the carbonate, which is green, the sulfate, which is blue. Now, are these the only compounds present that makes it green? The answer is no. That's not the case. Okay, there are more compounds in the Statue of Liberty, okay, which also contribute to the color. But these are the two main compounds that gives rise to the green color today. Okay, after speaking so much about this, so what's the point of talking about this? Hopefully you realize that the second reaction involves an acidic oxide with a basic oxide. That's acid-base neutralization. But the first reaction, where it goes from copper to copper 2 oxide, this is redox. So this brings us nicely to the concept that there are different types of reactions in the world. Okay? All the chemical reactions are different. But broadly speaking, there are 3 types of chemical reactions, broadly speaking. So what are the 3 types of chemical reactions? If you turn to the next page, the 3 types are acid-base neutralization, which we have seen just now, where an acid reacts with a base to form salt and water. Precipitation is the second type of reaction. How do you know it's precipitation? Well, we learned this under QA and salt prep. You start with aqueous. Aqueous plus aqueous forms solid. The state symbols are a clue that it's precipitation. Okay? So the first 2 types of reactions, you have learned them under acids and bases. You have learned them under salts and QA. However, actually, the most common type of chemical reaction is redox. And that's why we are learning redox now. Redox accounts for about 80 to 85% of all chemical reactions. So many reactions are redox. As shown just now, rusting is redox. All right. Now, besides rusting, other reactions like combustion. Combustion is also redox. Okay. Acid plus metal is also redox. Okay, so many reactions are redox in the nature. Okay. Now, why is it so important to learn these three types of reactions? Because very commonly in MCQs, we will give you 4 options and we will ask you, which of the following is not redox? So what is not redox? Acid-base neutralization or precipitation. These two are not redox. So you must choose correctly in an MCQ. Okay. Now, so at the end of maybe the next session, we would have finished this table. Today, we are going to at least tackle the first 3. The first 3 definitions of redox, which is oxygen, hydrogen, electrons. All right. So, but there are 4 ways to define redox. We will cover all 4, but today probably we will focus on the first 3. Now, let's go straight into this. So how do we define redox? How do we know what is reduced, what's oxidized? Well, you got to learn the definitions. The first one is obvious. Oxygen. Oxidize means gain oxygen. Right? That's the name one. If it gains oxygen, it's oxidized. Okay? On the other hand, if you lose oxygen, you are reduced. Simple. The name tells you that already. So let's look at the example equation that I have given you here. Copper 2 oxide plus hydrogen gas gives you copper metal plus H2O. Okay, so this is a reaction that I've given you. Okay, so in this reaction, what is reduced? What is oxidized? Now, how do you actually do this? First, you need to realize that the substance that is oxidized or reduced must be a reactant. So what is reactant? Reactant is the starting material, meaning it must be one of those things on the left-hand side of the equation. So the answer cannot be copper, cannot be water, because those are on the right. They are on the products of the reaction. Okay, this is an important concept. It always applies in redox. The substance that is reduced or oxidized must be on the left. Okay, so now you look at the left of the equation. Which one loses oxygen? Is it copper 2 oxide or is it hydrogen? I think it's quite obvious. Okay, copper 2 oxide has oxygen at the start, but at the end, the oxygen is gone, right? So this is what we mean. Copper 2 oxide is reduced because it loses an oxygen atom and forms copper metal. At first, there was oxygen, now there isn't, right? There was oxygen, now there isn't. It has lost this oxygen atom. Okay, then what is oxidized? Well, what gained oxygen? Oxidized means gain oxygen, right? So you look between copper 2 oxide and hydrogen, who gained oxygen? Again, it's quite clear cut. It's hydrogen, right? At first, it's H2. At the end, H2O. That means it has gained an oxygen through the reaction. Okay? So important concepts that we have covered. First, the one that is reduced and oxidized must be on the left side of the equation. This is true for all redox, all definitions. Okay? Second main concept, you will realize that if one reactant is reduced, automatically, the one that's oxidized is the other reactant. So like copper 2 oxide is reduced, therefore automatically hydrogen is oxidized. That's why it's redox. In a reaction, you must have something that is reduced, something that is oxidized. Okay, so that concludes the first definition of redox. All right. Now, this definition, while useful, while intuitive, cannot cover all the redox reactions. Why? Because not all reactions contain oxygen. There are some reactions that just don't have any oxygen, right? Okay, a good example is, let's say if I react acid plus metal. Acid plus metal, there may not be any oxygen in the reaction. So how then do you define redox if there's no oxygen in the reaction? And that's the reason why we need other definitions to define redox. Okay, now in the exam, which definition of redox should you use? Well, the question will state. The question will tell you using oxygen atoms, using loss and gain of oxygen, explain, blah, blah, blah. Okay, so the exam will tell you which redox definition to use, which is to say, you just have to learn all four and look at the question and see which definition they want you to use. All right. So if oxygen alone cannot define all the redox reactions, we need more definitions. So the next one is about hydrogen. Hydrogen. So now look, hydrogen lost, it's oxidized. Whereas if hydrogen is gained, the substance is said to be reduced. So immediately you see, oh my gosh, hydrogen and oxygen, the definitions are opposite of each other, right? In oxidation, oxygen is gained, but hydrogen is lost. In reduction, oxygen is lost, but hydrogen is gained. So when you study, you need to pay attention to these patterns. You need to recognize that, okay, this is a potential source of confusion. I need to get it clear. Oxygen and hydrogen are opposites of each other. Meaning, if oxidation is gain of oxygen, it must be loss of hydrogen. Okay? Now, this works very well because many reactions contain hydrogen inside them. All right, so let's take a look. So this is an example, okay? Chlorine plus HI, hydrogen iodide, gives you iodine, plus HCl. Okay, so just by looking at this reaction, again, you need to tell me what is reduced, what is oxidized. So again, your answers must come from which side? Is it the left side or the right side? So you look, you must always remember the answer, what's reduced, what's oxidized, what's on the left. So what's on the left? Chlorine, HI. Right? So now you got to decide, okay, who is reduced? So you got to think, reduction is gain of hydrogen. So who gained hydrogen? It's quite clear, right? Chlorine is reduced as it gains a hydrogen atom and forms HCl. Okay, at first there's no H, but at the end, the Cl and the H come together, right? Next, what is oxidized? Well, automatically, like I said, if Cl2 is reduced, the one that's oxidized is HI. And that makes sense because at first, H and I were together, but it lost a hydrogen to form I2. There's no more hydrogen at the end, right? Attached to iodine. Now, so a few things before we move on. Okay, so I'm sure you realize these two definitions are not difficult. I'm sure you could master them just by reading them and thinking through them. But importantly, you notice, I have written the formula out as opposed to writing chlorine is reduced. Okay, there's a reason for this. When I say chlorine, it's not immediately clear. Are you referring to the atom or are you referring to the Cl2 molecule? Right? Quite obviously, over here in the reaction is Cl2. Okay? So you are giving more information when you actually write the formula out. Because by writing the formula out, you're specifying that, oh, it's Cl2. You're not talking about just the atom itself. All right? Next, you realize that there is a 2 in front of the HI. Obviously, by now, you know that the 2 in front is to balance the equation. Do you write the 2 HI into the answer for redox? The answer is no. You don't, right? You just want to say which substance is oxidized. The substance is called Hi. The substance is not called 2Hi. The 2, it just gives you the mole ratio, which you need for mole concept. Okay, so you need to know when to put the 2. The 2 in front is not part of the formula. Okay, whereas the 2 at the bottom is part of the formula. All right. Now, before we move on, okay, I just want you to look at this page and ensure that you have understood oxygen and hydrogen. And I would like to open the floor to questions before we move on to electrons. Okay, because this electrons is a whole new ball game. Okay, so let's talk about oxygen and hydrogen first. Do we have any questions as to why we write things in this way? You can type in the chat as well. Okay, Jet, please go ahead.
Why the left hand side?
Why the
not?
left hand side, is it?
Oh, never mind.
Okay, no, that's a good question actually. That is actually a good question that we should solve now, right? Now, why the left-hand side? Now, the left-hand side of any equation gives you the reactants, right? The starting substances. So you could ask yourself, in a reaction, what is reacting? The ones that are reacting are the reactants, right? That's why it must be the left-hand side. Okay, so what is reduced, what's oxidized must be the left-hand side, because that's what is reacting. Okay, and actually this is a common MCQ, but maybe less so for pure chem. For combined science, they always like to test this. What is reduced and what's reduced in a reaction? And then the ABCD, right? They will put the 4 substances. 2 of them are reactants, 2 of them are products. So I always teach my combined science students, whenever you have a redox question, MCQ, and they ask you what is reduced or oxidized, you must learn how to eliminate the options. Okay, what is reduced and oxidized must be from the left-hand side. It cannot be the right-hand side ones. So those right-hand side ones can just cross out. They won't be the answer. Okay. Okay, so any more questions? If there are no more questions, let's not flip the page yet. Let's look at this reaction, okay? Chlorine plus Hi forms I2 plus 2HCl. This is redox, right? It is redox, we have shown that. However, this reaction also has another name. What name is this reaction? What type of reaction is this besides redox? Look at the elements. Chlorine, Hi, iodine, right? So which group are these elements from? Well, chlorine is group 7. Iodine is also in group 7. So what reactions did we learn for group 7? Which chapter did we learn group 7 even? We learned group 7 under the latest chapter on periodic table, right? So now let's think back. What kind of reaction do the group 7 elements undergo with each other? Okay, let's get someone to answer. All right, Jamie, do we know what type of reaction is this? Involving the group 7?
Displacement.
Displacement, great. So now do you realize, oh my goodness, this means that displacement is also a type of redox reaction. So just now we mentioned rusting is redox, so is displacement. Okay, now how do I know it's displacement? You can recognize displacement when you see the elements, chlorine reacting with iodine in a compound, right? So you got 2 different group 7 elements reacting with each other. So how does displacement work? Let's recall. Displacement is where the more reactive element displaces the less reactive element from its compound. So this is about reactivity of group 7, right? So clearly it's a competition between chlorine and iodine. Who is more reactive? Chlorine or iodine? Let's think. Okay, maybe Andre, which one is more reactive? Chlorine or iodine?
Chlorine.
Chlorine is more reactive. Now, how do we actually know that? Because for group 7, the reactivity decreases down the group. It gets less and less reactive down the group. Chlorine is on top, above iodine, therefore chlorine is more reactive. And you can see that because chlorine can displace iodine from Hi, right? So at first the I and the H are together. Chlorine comes in and displaces iodine out. Okay, so that's how displacement works. And this works because chlorine is more reactive than iodine. So it can displace iodine from Hi. So at the end of the day, the products formed are I2 and HCl. Okay, now why do I do all this extra info? It's not extra info, right? When you learn chemistry, don't just learn chapter by chapter. This is also the reason why I don't find the topical TYS super helpful, because you need to be able to link chapters together. If you notice my end of year exam, paper 2, every single question is a mixture of chapters. And that is deliberate, because for the O-level Pure Chem exam, you will not see a whole question on one chapter. It's not one question, one chapter. It doesn't work that way. One question will typically have 3 or even up to 5 chapters. So you can see now, redox is very easily combined with group 7. Group 7, we learned it in periodic table. So this is one way to test it. Now, you have learned displacement for group 7. In the next chapter on metals, you'll learn displacement of metals. So redox is very effectively combined with the chapter on metals as well. Okay, so you need to know the concept. Displacement is a type of redox reaction as well. Okay, so displacement is also redox. Okay, now if you have forgotten displacement and group 7, the reactivities, please go and revise periodic table, okay, chapter 16. Now, let's move on to the next one. The next one is more complicated. So obviously, we have finished oxygen, we have finished hydrogen. So as mentioned just now, maybe the reaction don't have oxygen, right? Similarly, maybe the reaction doesn't have any hydrogen in it. Does it mean it's not redox? No. We can define redox in other ways. A good way is electrons. And actually, this is one of the more commonly tested ones. Okay? This definition of redox is more commonly tested compared to oxygen and hydrogen. Now, how do you define redox in terms of electrons? Well, loss of electrons is oxidation. So if something loses electrons, it's oxidized. On the other hand, if something gains electrons, it's reduced. Because this is so important, we have even come up with an acronym for it. The acronym is OIL-RIG, OIL-RIG. Oxidation is loss of electrons, reduction is gain of electrons. Okay, Ken? So now you think, oh, so this is another way to define redox. And this is super good, right? Because I know that electrons are involved in chemical reactions. We have learned this since bonding, right? Certain things lose electrons, certain things gain electrons during a reaction. So this is a really commonly applied definition of redox. So this can be commonly tested. So now you're going to think, okay, so what loses electrons? Well, if you think back many chapters ago, you have learned that sodium 281, 1 valence electron. So it loses that 1 valence electron. Magnesium 282, 2 valence electrons. So it loses 2 valence electrons, right? So quite obviously, metals in general lose valence electrons to form positive ions. So in case you have forgotten, metals lose valence electrons. And at the end of the day, after losing valence electrons, the ion form are positive. Positive ions are also known as cations. So now you relate this, whatever you learned under ionic bonding, you now relate it to redox. Oh, so if it's lose electrons, that means it's oxidized. So quite clearly, the answer is B. Based on the definition, metals are more easily oxidized compared to non-metals. Metals are more easily oxidized. Why? Because they have fewer valence electrons than non-metals, right? Sodium, group 1 valence. Magnesium, group 2 valence electrons. So this is fewer valence electrons than, say, chlorine. Chlorine, 7 valence electrons, right? So if they have fewer valence electrons than non-metals, they will have a higher tendency to lose valence electrons. And like I said, when you lose electrons, it will form positive ions. Okay, so this is an important concept. So now you realize that, oh, metals lose valence electrons. So this is oxidation of the metal. Okay. Now, you realize that this concept is something you have learned in ionic bonding. When you first learn ions, actually this concept was taught to you, just that we have not linked it with redox. So now you need to link it with whatever you had done previously in term 2, you know. Okay, so that's typical of chemistry. If you do go on to do more chemistry, be it in poly, be it in JC, if you do more chemistry, you must learn how to link back to what you have learned. That is how you build a coherent picture of the subject. Okay? Now, so another new thing in this chapter is, okay, so now that I know that sodium is oxidized to form Na+, right? How do I write the half equation for it? Well, you can see the half equations are quite easy to write. It's not difficult to write. You started with Na. You ended off with Na+. So Na, Na+, Na, Na+. But how does it form Na+? It must have lost an electron, right? Lost one valence electron. So when you lose the electron, where does the electron appear? Well, losing an electron is like setting the electron free, right? Setting the electron free means the electron is on the right-hand side. So if the electron is on the right-hand side, that means lost electrons. Okay, because you have lost it. You have set it free. Okay, so whenever you see electrons on the right-hand side, it means that the substance has lost electrons. So the substance is oxidized. Okay, so you can see same for magnesium, but the difference for magnesium, of course, is magnesium has 2 valence electrons, so we write 2E minus. Okay, so electrons are represented as E minus. Okay, so sodium loses 1 valence electron, magnesium loses 2, the 2E minus. Okay. Now, why is this important? Because later on, in a later chapter on electrolysis, you will need to write these equations yourself. Okay, so usually for combined science, I will not focus on the half equations. I will just introduce it and move on. But for pure science, you will learn electrolysis as a chapter. And a very big part of electrolysis relies on you being able to write these half equations. Okay. Okay, so up to this stage, I think it's quite clear cut. So we have dealt with metals. Metals tend to lose valence electrons to form positive ions. Lose electrons means metals are oxidized. Okay, now let's go to the reverse. Obviously, the reverse of metal is non-metal. So for non-metal like fluorine, chlorine, quite clear cut, they will gain valence electrons. This is quite obvious. Fluorine, 2, 7. Has to gain 1 valence electron. Chlorine, 287 has to gain one valence electron to form ions. So you have learned, if they gain electrons, gain of electrons is reduced. So non-metals are more easily reduced. Okay, so non-metals are reduced because they have more valence electrons. Than the metals. Right? So like group 7, they have 7 valence electrons, which is a lot more compared to say sodium or magnesium. So if they have more valence electrons than metals, so they will have a higher tendency to gain valence electrons to form negative ions. Okay. So please copy this down, let this sink in. Okay, and this is where most students for pure chem will start to get confused. But isn't fluorine already F2? Why would it still want to gain electrons? Surely the fluorine has already shared electrons with another fluorine, so the outermost electron shell is already fully filled, right? Well, that's true, right? That's what we taught you. It shares electrons. It should have a fully filled outermost electron shell in F2, in Cl2 already. But we also know that in the presence of a metal, for example, let's say I mix and react fluorine, F2, and sodium together, things change, right? Fluorine on its own, great, okay. But what if fluorine is now paired with a metal, like sodium? Sodium can lose electrons, right? So sodium can lose the electron, and the electron goes to where? Well, fluorine is ready to accept it. Because fluorine, in the presence of electrons around, can start to accept the electron, can start to gain the electron. Okay? So even though F2 on its own is already a stable, fully filled outermost shell because it has shared electrons, in the presence of a metal like sodium, magnesium, these metals can lose their electrons and the electrons can be shot towards fluorine. So what happens is that the covalent molecule, the F2 molecule, the covalent bond will break, and then the fluorine atoms can now accept the electrons, can now gain the electrons. Okay? So let's not have this misconception. A lot of students are just confused. Hey, I thought covalent already stable, fully filled outermost shell. How come still can accept electrons? Well, it's possible if there is a metal that can lose electrons around. And that's the reason why Cl2, F2 on their own, it's okay. But the moment you put a metal in, the drama changes. All right? So this is a bit like social dynamics, right? Sometimes in your class, actually you're okay with your friend, but then maybe someone new comes in, then you don't feel so okay anymore. All right, things may change. Okay, it's works the same way. All right. All right. So you notice I spent quite long on this because I want you to be clear about the half equations. My next thing is, do you realize that for the fluorine and chlorine, it's very important to balance. Now, to balance the equation means obviously you need to have 2F minus, 2Cl minus, right? Obviously. If not, it will never balance. Okay? If you have 2F minus, naturally you must have gained 2 electrons. Obviously, each F minus is formed when the fluorine gains 1 electron. You got 2F minus, 2 electrons gained. Okay? So importantly, you need to know that the electrons are on the right-hand side, meaning electrons gained. Oh, sorry, left-hand side, sorry. The electrons are on the left-hand side. So electrons are gained, they're accepted in. Okay, just take note. The electrons are on the left-hand side. So now you look, these two are opposites again, right? So in chemistry, you always learn opposites. So now you're going to learn, when you revise, these are opposites, opposite concepts. So you need to know, okay? And of course, this adds on to your understanding of what it means to be a metal, what it means to be a non-metal. Okay, finally, I have 10 more minutes. Okay, I'm able to talk about half equations. So I keep on using about half equation, half equation. Half equations, are they just not ionic equations? Well, the answer is yeah. Half equations are like ionic equations, right? They have ions inside. They have charges. But what distinguishes a half equation from an ionic equation is that half equations show electrons. Half equations show whether the electrons are lost or electrons are gained. Okay? So when we ask you for the half equation, we mean the equations which show you whether the electrons are lost or gained. Okay? Now, why do you think they're called half equations? Obviously, half equation means, is it complete? Half, is it complete? No, right? That's why people say I need to find my other half, right? To make myself complete. So similarly, half equations are not complete. So what do you need to make it complete? Well, half is not complete. Maybe two half equations will make the reaction complete. And that's the idea. It's called half equation because it only shows you half the story. For example, it only shows you oxidation. Then where's the reduction? Oh, the reduction is another half equation. Okay, so remember, going back to what I said at the start of the lesson, in every redox reaction, there must be something reduced, something oxidized. So the half equation tells you only half the story, the oxidized part or the reduced part. In reality, you must have the two half equations to make the overall complete reaction. Okay, now I will not go into how to write the overall equation yet. That one we will do in the later chapter on electrolysis. But for now, I really want you to learn there's something called a half equation. The half equation shows you electrons gained and lost. And I want you to know if electrons are on the right-hand side, it means lost electrons. If it's on the left-hand side, electrons are gained. Okay? Now, going on, and we will probably end at this page. Now, there are question sets which I'll not go through every question. Okay? Now, for today, I'm just gonna go through A and B. Because the rest, I would like you to try on your own over these very long holidays. Now, you realize that this is the exam question. The exam question will be like that, right? Explain whether the underlying substance is oxidized or reduced in terms of electrons. This is exactly what I was talking about. The question will specify which definition to use, right? So today we learn oxygen, we learn hydrogen, we learn electrons. So which definition should you use in your answer for exam? Well, the exam question will tell you. So you need to pay attention to the instruction, okay? Now let's try A and B. Let's look at A and B. Okay, just A and B today. Okay, now I trust that you can see my screen and you can also see what's on your notes, all right? I want you to have a think about it and I'll get some of you to tell me whether the underlying substance is reduced or oxidized. So in case you forgot, oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. How do you know whether electrons are lost or gained? Well, look at the equations. You will know from where the electrons are. Okay, when you are ready, can you give me a thumbs up so that I know that you are ready and we can move on? to go through A and B. Okay, you just need to think about it. I'm not expecting you to give me an answer, like full answer straight away. Okay, thank you to the 2 people who have raised, give me a thumbs up. The rest, are we following? Okay, thanks, Jinkang, Audric, Yixuan, Estella, Christine, Jamie. Okay, thank you. Let's begin. Let's look at A. Now, this is a half equation, obviously, because you can see electrons, right? Can see electrons means half equation already. Okay, let's start. Now, the underlying substance, they want underlying substance, so Cu in this case. Okay, your answer must always be Cu is either oxidized or reduced, right? So let's think through it. Let's look at this equation. Do you think Cu has gained electrons or has it lost electrons? Okay, so let's ask someone. Okay, Rishi, do you think Cu has gained or lost electrons?
Lost electrons.
Lost. How do you know that, Rishi?
Because it's in the right hand side.
What is in the right hand side?
The electrons.
Yes, the electrons are on the right hand side, right? Okay, thank you, Rishi. So yes, Rishi is right. Cu has lost electrons. So Yixuan, is Cu reduced or oxidized?
Oxidized.
Okay, so let's complete sentence. Cu is oxidized as it has lost electrons. But let's not end here. Now, I always like students for Redox to give the answer in this format. You lose electrons already to form what? What did it form? Jinkang, what did it form? It lost electrons to form what?
Copper 2 plus.
Yeah, okay. So instead of spelling out copper 2 plus, okay, just write Cu2 plus. Okay, ions, right? Ions. Okay, but minimally, can you please write Cu2 plus? Okay. So this is the format of your answer. Now, for redox, it's very important to stick to a structure in your answer. Always tell me what is oxidized or reduced, why, based on definition, what it forms at the end. Please adopt this structure. Do not deviate from this. When you deviate from this structure, your answers will always lack some detail. Okay? Now, how come over here it lost 2 electrons? Why did it lose 2 electrons? Can't it just lose 1? How do you know it lose 2? Well, the charge tells you, right? 2 plus. Copper 2 plus. To form 2 plus, you must have lost 2 valence electrons. Okay? And okay, so now Mr. So got more question to ask. So at first copper got no charge. Now copper got charge 2 plus. So the charge has become more positive. Okay, hopefully we realize that. How come the charge has become more positive on copper? Because you lose electrons. Lose electrons, positive charge. Okay, so that's part A. Are we okay with this? Okay, if you're okay, give me a thumbs up so that I know that you have grasped whatever I'm saying. Okay, you might think that I'm going very slowly. That's because it starts right? I should go light and I should ensure that you understand little bits of what I'm saying. Okay, great. Okay, let's go next one. B. Now B, you realize, Cu2 plus, we start with Cu2 plus. Interesting. Okay, so let's look at B. Do you think the underlying substance, in this case is Cu2 plus, the underlying substance, has it gained or has it lost electrons? All right, Estella, do you think Cu2 plus has gained or lost electrons?
Lost.
lost electrons. Lost electrons, the electron should be on which side? So Estella?
Gain electron.
Okay, gain electrons. Okay, so how do you know it's gain electrons? How can you tell? Electrons are gained when the electrons are on the
Left hand side.
left. So when you see the electrons on the left hand side of the arrow, right? On left hand side means electrons are gained. Good, thank you. Okay, so Jiabao, can you tell me, is Cu2 plus reduced or oxidized?
Reduced.
Okay, reduced, thank you. Okay, let's complete the sentence. Let's complete the sentence. So Cu2 plus is reduced as what? Audric, how would you complete this sentence?
It has gained electrons to form.
Okay. To form? To form what?
Cu.
Cu. Okay, Ken, thank you. Okay, so now you'll be thinking, strange, right? Wow, so what is Cu? Cu is just copper metal, right? So at first it was Cu2 plus the ion, but it's now gained electrons reduced to form Cu, copper metal itself. Okay, no, copper metal, we never ever say copper 2 metal, wrong. Got no 2. How come got no 2? Because the metal got no charge. It's just copper. Okay, let me just write nicely. Cu is just copper metal itself. The metal got no charge. Okay. So what do you notice? As it go from Cu2 plus to Cu, the charge on copper became less positive. At first it's 2 plus. Now no charge already. Okay. How come become less positive? Because you gain electrons. Whenever you gain electrons, you become less positive. Because electrons themselves are negatively charged. Okay. Ken? Now, don't you realize that A and B are just the opposites of each other? If you look at A and B closely, what's the difference? The only difference is that I've swapped the reactants and products, right? So for A, I started with copper metal, becomes Cu2 plus. That is oxidation. Cu is oxidized in A. In B, I started with copper 2 plus, Cu2 plus. It gained electrons and got reduced to form Cu. So these are actually opposites of each other. But because they are opposites, you can now see that, oh, one is oxidation, one is now a reduction. Okay? Ken? So I hope you recognize this. Okay? So what have we learned today for electrons? Importantly, you have learned oil rig. Oxidation is loss of electrons, reduction is gain of electrons. How can you tell from a half equation if the reaction involves loss or gain of electrons? The positioning of the electrons is important. If the electrons are on the right, electrons are lost. If the electrons are on the left, electrons are gained. All right. Now, what I've written in green, which is on charge, it will be an important concept because we don't always give you the half equation. Certain questions, if you look at set 2, the next page, set 2, I don't give you the half equations. I'm giving you the ionic equation. So how can you tell now whether it loses or gains electrons? For set 2, you can't tell, right? There's no electrons shown because I've not drawn the half equations for you. Well, you can still do the question because you look at charge. Has the charge on silver, for example, become more positive or less positive? Quite clearly, Ag plus became Ag, It became less positive. If the charge becomes less positive, has it lost electrons or gained electrons? So Jamin, do you think Ag plus has lost electrons or gained electrons?
Gain.
Gain, right? Because when you gain electron, become less positive. So now you know Ag plus gained electrons. So Ag plus is reduced. It gained electrons to form Ag. So now let's do the reverse, right? So what is oxidized? Jet, what do you think is oxidized in 2A?
Copper.
Yeah, copper. So we write Cu. Cu at first no charge, right? Then now 2 plus, meaning the charge became more positive. So Cu is oxidized because it lost electrons to form Cu2 plus. You notice that I'm perfectly okay with writing chemical formula. Usually for redox, we just use the chemical formula in the equations given to us. It is better than spelling out copper. Okay, can? All right, so you can see for set 2, right, it's not half equations anymore, it's ionic equations. And that's the reason why you need to be familiar with charge. If the charge becomes less positive, like Ag plus, then it must have gained electrons, it must be reduced. If the charge becomes more positive, it's oxidized because it lost electrons. Okay, now that concludes the start right for today. Tomorrow, we will continue with redox and we will go through oxidation states, which is another major concept, but it's actually related to charges. All right, so tomorrow we shall continue at 3:30. All right, 3:30, we will continue on oxidation states. Okay, for the practice, you can do the rest of question set 1 and set 2 already. Okay, so it's good for you to try. All right, so I shall stop the recording here.